Welcome to my circuit lab. This week we're going to have a blast with Play-Doh and circuits. We'll learn how to make conductive and insulating Play-Doh and create series and parallel circuits with LEDs. Let's dive into the world of Play-Doh circuits. First, let's make our conductive Play-Doh. Here's what you'll need. Mix all the ingredients in a medium-sized non-stick saucepan over medium heat, stirring continuously until the mixture thickens and forms a ball. After heating the mixture, we'll let it cool before proceeding to knead. After kneading, we'll add another half cup of flour to reduce stickiness. When we mix flour, salt, and water, we create a mixture where the ingredients are combined but not chemically changed. If you mix salt and flour, they would remain in their original form and could theoretically be separated again. However, when we add water and knead the mixture, we get a new substance, Play-Doh. This transformation happens because of chemical reactions between the ingredients, making it hard to turn the Play-Doh back into its original components. When making Play-Doh, adding water allows the proteins in the flour to stick together, while salt strengthens this bond and prevents spoilage. Oil coats the ingredients to keep the dough from drying out, and the food coloring spreads out to give the dough its color. Next, we'll make insulating Play-Doh. The ingredients needed are shown here. Begin by mixing the flour, sugar, and vegetable oil into a mixing bowl. Stir until all of the oil is absorbed. After mixing, pour small amounts of purified water into the mixture and stir until the water is absorbed. Repeat this until a ball forms. After your ball has formed, remove it from the bowl and knead it on a lightly floured baking sheet. Just a note, be extremely careful when you're adding water because this can get way too slimy too fast, and then you have to add a bunch more flour to get it to the desired state. Next, I'll be moving on to the series circuit section of the lab. First, cut your battery packs off of your LED strips, and then cut your LED strips. Expose wire using wire cutters on both the packs and the LEDs. Next, wire all three battery packs together as shown. Next, insert a light as shown, and then turn on all three battery packs. LEDs only allow current to move in one direction, so if the LED does not work, turn the LED around. We used the same setup for the second example, except for we used 3 balls of conductive Play-Doh. In this example, the lights shine much dimmer than the last. In the fourth example, we use 4 pieces of conductive Play-Doh. The lights are even dimmer than before, and for some reason they start flashing. In the last example, the lights don't turn on because the circuit isn't complete. When you hold your finger across these 2 balls, the lights turn on dimly. Now we redo the circuits with our non-conductive Play-Doh. In the first one, the light turns on still, but in the second example, the lights are even dimmer than the first time. In the third example, the lights are barely visible, and when we remove this one, the lights turn off completely, and your finger barely powers it. In a simple circuit, electricity flows from the positive end of the battery through the conductive Play-Doh and into the LED. The LED only allows current to flow in one direction, which is why it might not light up if it's inserted the wrong way. Once the current passes through the LED, it flows back to the negative end of the battery, completing the circuit. This flow of electricity makes the LED light up. Next, I move on to the series current. Both lights are shining at the same brightness. When another light is added, they shine a little bit dimmer, but it's barely noticeable. Next, I'll remove one light from the circuit. The 2 lights get a little bit brighter. Next, I'll repeat with the non-conductive Play-Doh. In the first example, the light shines less bright than it did with the conductive Play-Doh. Once a second light is added, they shine even less bright. Now I'll add a third light. Again, they shine dimmer. When one is removed, they shine brighter again. In a series circuit, each component is connected end to end, forming a single path for the electric current to flow. This means the same current flows through all components. When we add more LEDs in series, each LED adds its own resistance to the circuit. The total resistance increases, causing the current to decrease. This is why additional LEDs in a series circuit might appear dimmer, as the same current is shared among more components, reducing the amount of current each LED receives. Next, I'll be moving on to the parallel and series circuit. In this example, all three are flashing. When we add this one in the middle, it makes it into a series circuit, and only this one flashes. When repeated with the non-conductive Play-Doh, and I add my fourth light in, all four shine. They don't shine as bright as the conductive Play-Doh, but this one, for some reason, does shine when the conductive Play-Doh doesn't. In a parallel circuit, each component is connected across the same 2 points, forming multiple paths for the electric current to flow. Unlike a series circuit, each path in a parallel circuit can have its own current. This means that if one LED burns out or is removed, the others can still light up because each LED has its own separate path to the power source. The total current in the circuit is the sum of the currents through each parallel branch. This setup ensures that each LED receives the full voltage of the battery, so they all light up brightly, regardless of how many are in the circuit. Today, we made conductive and insulating Play-Doh and built series and parallel circuits using LEDs. We learned how current and resistance affect the brightness of LEDs. This concludes our series on making circuits with Play-Doh. I hope you enjoyed these experiments and learned a lot about electricity and circuits. Thanks for watching.